So a few announcements before we get into the class material. The homework 1 has been posted on Piazza. It is due on September 11th, Friday, in 1 week time on Gradescope. Studio 1 is also posted on Piazza. Can you guys mute yourself? I hear a few clicking sounds. Thank you. All right, so Studio 1 is posted on Piazza, due on Gradescope, and you also need to get checked off during studio times. It's due on September 16th, so you have a lot of time, but I strongly recommend that you start early. So start looking at the studio. I've also posted a video regarding Studio 1 information. Look at that video to help you with how to tackle Studio 1. Quiz 2 is on Gradescope. That's all right. You guys need to mute yourself. All right, thank you. Quiz 2 is on Gradescope for class lecture 2. So do that sometime today. The academic integrity and digital tools acknowledgement forms are also due on Gradescope on September 8th. So I hope that many of you have already done it. Close to 60% of the class has already done this. It takes a few minutes to get through it, but some of you have not. So please finish that as soon as you can. Okay. Any questions or concerns about announcements here? You can always ask for questions or clarifications in the CoCO WebEx team space or on Piazza. Studio 1 will
One quick
be
question on the chat box.
Studio 1 is going to be individual assessment, but after that you will be put into teams of 2. So while you are doing Studio 1, try to look for a partner in your own studio section. So studio section A, try to look for a partner in section A so that you can go to the studio at the same time. So think about that during Studio 1, because from Studio 2 onwards, you will be submitting this as a group of 2 students. Okay, so I think I've addressed the question. I'm going to move on. I'm going to switch off my camera here just so that we have all the bandwidth for the lecture slides and there are no glitches. Of course, I can pray for that, but WebEx will continue to do its thing. So we will continue with base conversions. This is where we left off in the previous class, so we'll pick it up over here. How do you convert 58 in base 9 to base 5? 58 belongs to base 9, right? Because symbols are from 0 to 8. Those are the symbols in base 9. So 58 is a base 9 number. So the question is valid. It's correct. Now, how do I do this? Well, first I would do 9 to 10, and then I would bring it from 10 to 5. So let's do that. How do I do 58 to 10? I can say 8 times 9 raised to 0 plus 5 times 9 raised to 1, which is going to give me 53 in base 10, right? So once I've got 53 in base 10, the next step can be from base 10 to base 5, which is going to be divide 53 successively by 5 and record the remainders. So 10 times is going to give me 50, the remainder is 3, and then again if I do divide by 5, 5 times 2 is 10, and the remainder is 0. That's it. So I've got 203 as my answer. And just to check, 2 and 0 and 3, they are all belonging to the base 5 system. Base 5 will have what? 0, 1, 2, 3, and 4. And 203 belongs to that set. So that's good. So this is how you would go from 9 to 5 or 6 to 12. From any to any. You can use base 10 as your stepping stone to do this conversion. Now, let's start talking about a special case of number systems that are powers of 2. So for example, binary is what? 2 raised to 1. And then base 4, and then base 8, which is octal, base 16, which is hexadecimal. There is a very good property to convert among bases that appear as powers of 2. That's what we are going to talk about over here. So on this table on the right, we have all the hexadecimal symbols, 0 all the way to F. So 0 through 9, A through F, those are your 16 symbols. Their equivalent decimal numbers are also written in the rightmost column, 0 through 15. And then their binary equivalent is also written in the middle column, 0, 0, 0, 0, all the way to 1, 1, 1, 1. And in the previous class, I talked about how to do this in a very, very fast manner. The least significant bit, LSB, or the rightmost bit, is going to alternate, 0, 1, 0, 1, 0, 1, and so on. And then the next to that will go 0, 0, 1, 1, and so on. And then the next to that will go 4 zeros, 4 ones, 4 zeros, 4 ones. And then the most significant bit, the leftmost bit position, will have 8 zeros and 8 ones. And that's how you will have 16 unique combinations of zeros and ones. So you have got hex, binary, and decimal. And we can use this table to do all these conversions. So let's see. The example over here is convert this very long binary number to hexadecimal. And all you would have to do is start grouping the numbers from the right in groups of 4. Why groups of 4? Well, because each hex digit expands into 4 binary bits. So if I want to go from binary to hex, I would start to combine. I need to combine as groups of 4. And you need to do that all the way from the left, all the way from the right. So you would start here, go 0, 1, 0, 1. What is that? That's 5. And then you would go 0, 0, 1, 1. What is that? C in hex, because it is 12 in decimal. And then you would go 1, 0, 0, 0. That's 1. And then you would go this. That's B. And then you would go, all right, over here I'm missing something, right? So I can always add zeros to the left of the number without changing its value. 5 is the same as 0, 5 is the same as 0, 0, 5. So no problem, I can add zeros to the left. And when you combine that, now if you can see this, this will become 0, 0, 1, 1, which is 3. So your hexadecimal number here is going to be 3B1C5. That will be in hex. Right? Very easy. All you need to do is start grouping in 4s starting from the right. And if you need to add zeros to the left, you add zeros to the left. All right. I memorized this table, but what I'm really hoping for is you do this so many times that you almost remember it by default. All right. Let's do this. Represent coffee in binary. What is wrong with this question? Anyone? What is wrong with this? Yes, it is a 0, right? So this is a 0. It is not O, because O does not belong to the hexadecimal system. So this is C0FFEE, right? How do I do this conversion to binary? All I would need to do is expand, right? Expand each hex digit as 4 bits, 4 binary digits. So for C, I've got 1, 1, 0, 0. For 0, I've got 0, 0, 0, 0. For F, I've got 1, 1, 1, 1. For F, I've got 1, 1, 1, 1. And for E, I've got 1 less. Sorry. And then for E, again, I've got 1 less than F. That's it. Right? So converting between hex to binary, I hope you see that it is a very, very simple step, right? Just expanding each hex digits into 4. Why? Because each hex digit has 4 bits associated with it. 0 to F goes from, for binary, it goes 0, 0, 0, 0 all the way to 1, 1, 1, 1. All right. How about this way? How do you do this? Well, we have already looked at an example. Let's take a look at this as well. So I'm going to what? I'm going to group over here. Group in 4 bits, right? So if I combine these 4 bits here, I would get what? 0, 1, 1, 0. That's 6. Okay, so let's write 6. And then I've got another group here, which is 1 more than 10, right? 1, 0, 1, 1 is 11. So 9, 10, 11, 9, A, B. So I would write B6. You are right. Right? Perfect. So over here, I was grouping in 4 bits, starting from the right. And if you need to add zeros to the left, you can add zeros to the left to make it into a complete group of 4 bits. So on this slide, I have all the theory that we have just talked about written up, right? So if you want to convert between bases that are, for example, 9 and 5, you use decimal as your stepping stone, right? So you go from 9 to 10, 10 to 5. You can also go 16 to 10, 10 to 2, but that is a lot more work than needed. So for conversion between bases that are appearing as 2 raised to n, what you're doing is either grouping them into 4 bits or 3 bits or 5 bits at a time, depending on what that power of the 2 is, or expanding them for those many bits, right? So grouping them or expanding them, that becomes very, that can become very quick. Can we do 0x B6 in homework? I'm not sure I understand the question. So we just did that example over here. If you are saying, can I write it as this? Yes, you can write it as this. Yes. This is also okay. Both are okay. In fact, even you can write it like this, B8 in hex. That is also okay. So if you have 1 bit, then you have 2 possibilities, right? 0 and 1. That's your base 2. But you have 4 bits, you have 16 possibilities. That's your base 16. And similarly, if you have 3 bits, what is going to happen with 3 bits? Well, for 3 bits, you are going to have 0, 0, 0 all the way to 1, 1, 1, and that will give you 8 possibilities. And those 8 possibilities are going to be related to base 8 or octal number system. Let's continue with this coffee theme, right? Convert decaf to octal number system. So over here, what would I do? I would do base 16 to base 2 and then base 2 to base 8. That's what I would do. So how can I do base 16 to base 2? All I would have to do is expand into 4 bits each, right? So D is going to be what? D is 1 more than C. So 1, 1, 0, 1. E is 1, 1, 1, 0. C is 1, 1, 0, 0. A is 10. F is 1, 1, 1, 1, right? And done. Group of 4 bits, then groups of 3s. Perfect. So first step is done. I've expanded, I've done it in binary now. The second step would be to group into 3 bits starting from LSB, least significant bit, right, which is this guy. And I would move left. So if I started grouping them, let's do this in colors here. 3, 3, 3, 3, 3, and then I can always add a 0 there. So now when I write it as an octal number, for 111, I will have 7. For 101, I will have 5. For 010, I have 2. Next, 110, 6. 110, 6. 0113, 0113. That's it. That's your octal number. Now, clearly, this number has symbols that belong to the octal number system, right? 0 through 7. So that's good. That checks out as well. So that's how you could go from hexadecimal to octal. How would you do this? 8A, 9B to base 4. How would you do that? You would expand into 4 bits and then group into how many bits? Groups of 2. Perfect. 8A, 9B. And then groups of 2. 2. Let me just write that over here. So I've got 1, 1, 3, 1, 0, 2, 1, 2, 2, 2, 0, and 2. And I suppose you have guys get the idea now. So your answer will simply be 20222123. All right, let's move on here. Now there is a very interesting property that I want to demonstrate by using this table. So let's try to first fill out this table. What is decimal 1 in binary? 1. Good. What is decimal 3 in binary? 1, 1. Okay. What is decimal 7 in binary? 1, 1, 1. All right. What is decimal 15 in binary? Okay. I hope you now understand where we are going with this. Decimal 31 will be 1, 1, 1, 1, 1, and so on. How about 2 raised to n minus 1? As you can see, decimal numbers 1, 3, 7, 15, 31, and so on have a general form of 2 raised to small n minus 1, where n is the number of bits that you need to represent that number, right? So 2 raised to n minus 1, what do you think that is going to have in binary? N ones. Okay, that's good. String of is going to have 1, 1, 1, da, 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 all ones. That's going to be a string of ones. How many ones? N ones. Perfect. So if you have, say, n is 4, then 2 raised to n minus 1 is going to be 15, and you have got 4 ones to represent that, right, in binary. This is 10, this is 2. So the thing that I want you to take away from this slide is, if a number is of the form 2 raised to n minus 1, then in binary it is always going to be a string of ones, right? This is going to help with the binary arithmetic discussion that follows. Why do we need to do binary arithmetic? Well, we need a computer to do addition. We need a computer to do division, subtraction, floating point arithmetic. We need a computer to, or any digital device to do arithmetic for us. Without having arithmetic operations, we don't have any use for a computer to begin with, or even a calculator to begin with, right? So we would need to establish some rules in order to do arithmetic in binary. Why binary? Because the computer is going to deal with bits. It's not going to deal with decimal numbers. It's going to be dealing with zeros and ones. So the same way we have learned addition, subtraction, multiplication, and division with decimal numbers since elementary school, we are now going to see what kind of things we can take from that and what are the things we need to adjust in order for binary arithmetic to work out. So let's start to talk about that with a quick refresher with decimal. If you wanted to add two numbers in decimal, you can quickly come to an answer, 87, 56, add them up, 143, right? But let's try to kind of piece together each of these pieces. 87, right? 87 represented in position using positional significance, you have got that 8 times 10 to 1 plus 7 times 10 raised to 0. And similarly, you can represent 56 as well, right? 56 can be represented using positional notation that way. So when you are actually adding the numbers starting from the least significant position, the rightmost position, when you add 7 and 6, you get 13. Which number do you write as the sum and which number do you carry over to the left position? Well, 3 will be your sum. 1 will actually move on as carry to the next addition. In other words, the least significant bit of the addition will be the sum and the most significant bit of the addition will be the carry, right? So when you did this, the least significant came here, most significant went over there as carry, and so on, right? We are going to need that same concept of where should the sum go and where should the carry go when we go to binary arithmetic, which is the whole purpose of talking about a decimal addition. So let's do that. Now, so what are we adding? We are adding zeros and ones. So we need to understand what are all the possibilities when you add zeros and ones. When you add 0 and 0, you get a 0, right? No carry. Let me write that out. No carry. Actually, let's do this. Let's have a column for sum and let's have a column for carry. So this will be your sum and we will fill carries over here. So 0 plus 0, sum is 0, obviously carry is 0 as well. When you add 0 and 1, the answer would be 1, no carry. When you add 1 plus 0, similarly sum is 0, sum is 1, carry is 0. But when you add 1 and 1, what do you get? You get 2 in decimal. 2 in decimal is what? 1, 0 in binary. We just said the least significant goes as sum and the most significant goes as carry. So the least significant came in over here and the most significant went as carry. So you've got two outputs, sum and carry. This is adding 2 bits at a time, right? So only adding 2 bits at a time, you have got two outputs. So inputs are 2, outputs are 2. This is called a half adder. So this is a half adder or a modulo 2 adder, which is essentially adding 2 bits at a time. Will you always only need to add 2 bits at a time? No, you will need to add 3 bits at a time as well. Let's take a look at an example here. Suppose you are adding 1100 to 1111, right? Suppose you are doing this addition of binary numbers. When you are trying to add that, this requires the least significant addition requires, let me change this to 1. That requires a half adder. So 0 plus 1 would be what? 1 carry of a 0. But next, you see what happened here. A half adder was sufficient so far, but now we need the ability to add 3 bits at a time to move forward. 0 plus 1 plus 1. So we need a full adder that can add 3 bits at a time. And here it is. This is the full adder table. So you have got 3 bits of course, with 3 bits, how many possibilities are going to be there? 8 possibilities, right? 2 raised to 3, 8 possibilities. Why 2? Because we are talking about zeros and ones, binary. So you've got 3 numbers here in each row that are getting added. All 8 possibilities. For each of them, we have the sum, just the same way as we had earlier, and we also have a carry. So all the other carries are 0. Let me write that down. Carry is going to be 0 here, 0 here, 0 here, 0 here, and everything else has a carry. So for example, let us take a look at the last one. All right, last one is interesting. 1 plus 1 plus 1. What is that? 3. 3 in decimal is what? 1, 1. That's why you have got the sum as 1. That's why you have got the carry as 1. So what is the carry on the left of the table? So what is the carry on the left of the table? Oh, that's a very interesting question. So you see what happens is this. When you start adding numbers, what is this guy? Carry, right? Carry from previous position. And there will be a carry out from here. So let's suppose we are focusing on this 0 plus 1 plus 1. That's 2. 2 is what? 0, 1. 0, 1, right? So this is your carry out. This is your carry in. So we have essentially two carries. I think I'm okay. At least on my side. Right? So when you add 3 numbers, the carry input refers to the carry in from the previous addition. So carry in from the previous addition, and there is a carry out to the next position. So I hope that answered your question. Good question there. So let's see. Let's just put it in like this. Carry in and carry out. So that's your full adder table, right? So 3 inputs, 2 outputs. For half adder, you had 2 inputs, 2 outputs. Now with those 2 adders, half adder and full adder, we can start looking at binary addition. So when you are trying to add 5 and 3, what are you going to get? Let's take a look. I'm writing the carries over here in green. How would you simulate this with a circuit? Let's hold off on that discussion for now. I will be talking about that later. There is a way to do this. You would have to write expressions for that. I will talk about that in the next one. But right now I'm focusing on binary arithmetic. So stay tuned for that discussion about how you would design a half adder into a circuit form, into a schematic form. Are we allowed to put zeros as a placeholder on the leftmost side of a number when adding? Only, yes, but only when you are doing that for positive numbers. Only for positive numbers you can do that. So the moment so far we have been talking about unsigned numbers, only positives. When we start talking about negative numbers, then you will be allowed to put ones as the placeholder on the leftmost side when you are doing any addition or subtraction. So it will be ones for the negative numbers. We'll talk more about that as we get close. So actually over here, you see I've added a 0 there. So let's see. When you're trying to add, you've got 1 plus 1. A half adder is fine. Or I can just assume that the initial carry is 0 and then use a full adder. Full adder, full adder, and full adder. So how many full adders do I need over here? I think I need 4 full adders to do this. More about that discussion also coming up later. So let's see. 1 plus 1. Initial carry is 0. 1 plus 1 would be sum is 0, carry goes up top. 1 plus 0 plus 0. 1 plus 0 plus 1. That's 2, which means 1, 0. 0 goes here, 1 goes up to carry. 1 plus 1 plus 0. 2. 2 is 1, 0 in binary. 0 goes here, 1 goes here. And then this carry has nothing to add on with, so it comes down to as 1. Right? So that's your addition of 5 and 3, but this happened as this happened using a full adder, 4 full adders. We paid attention to sum, we paid attention to carries, and you have got the right answer. 1, 0, 0, 0 is 8. So you've got the right answer, the expected answer. But here is a kicker I want you guys to start thinking about. How many bits do you need to represent 5? How many bits do you need to represent 5? At least 3, right? All right, good. How many bits do you need to represent 3? 2. So if I need 3 bits to represent 5 and 2 bits to represent 3, maybe I can just say, all right, fine, let me use 3 bits to represent the numbers that are getting added. Right? I'm being very generous here. I say, let us use 3 bits to represent the numbers that are getting added. And if I limit the number of bits, guess what happens? 101 plus 010 will give you 000. If I limit the number of bits, do I get a correct answer? No. What did I get? I got a 0, right? So if I was limiting the number of bits, I would get, oh, sure, overflow. Perfect. Okay, so you guys are ahead. All right, I'm trying to reach there. If I limit the number of bits, I could get into trouble. So that's something that I want you guys to notice here. We are not limiting the bits just yet. But note that if you limited them, then we would have some issues that we would need to address. Okay, so you have a computer, right? It's a 64-bit computer. So if you have a 64-bit computer and you're using some number of bits to represent numbers, right? So for example, you would use, say you're using the whole 64 bits to represent one number. So if you have 64 bits to represent one number and 64 bits to represent the other number, your answer will also be a 64-bit number, you see? So your device itself will put a limitation on the number of bits. So right now we are not talking about those limits formally. I'm just introducing the idea that if you had only specific number of bits that you could store or use to represent numbers and go through this addition process or any other operation, then we might end up in trouble. No, I mean limiting the number of bits that are used to represent the numbers and the result. So if I said you can only use 3 bits to do the numbers and the sum, to do the numbers and the result, then we would get an incorrect result. We would still be able to represent the numbers, but we would not be able to represent the result. But if I said, okay, you have 4 bits, then everything is fine. 4 bits, you get the numbers and the result. That's fine. Yes. Right? Think about it like this. You only have 3 slots. If you have only 3 slots that you can use for the numbers and the answer, you have got 101 here, sure, done. 011, sure, done. But for answer, you would get incorrect, right? Because 1 would be out of bounds. So it's called a data overflow. We will talk about that more formally in just a bit. But I thought I would introduce the idea of getting an incorrect result if we started limiting the number of bits that we use. All right, let me cross out of this here so that later there is no confusion. We'll address that in more detail. How about subtraction? Well, 95 minus 16, your expected answer is 79. Again, we are not limiting the bits over here. What would you need to do? Instead of having sums and carries, what will you have here? You will have differences and borrows. But the borrows over here, we are representing as an explicit -1 to the left position. Borrows are shown as explicit subtractions of -1 to the left position over here. And you can again use positional notation to represent 95, to represent 16, and then you can do the differences. You can use the borrows wherever necessary and then find the difference result. In this case, you get 79. Okay. How would we translate this into binary? That's the question. We had half adder and full adder for addition. Now we are going to have half subtractor and full subtractor. So 0 minus 0. Let me do this as two things. Difference and borrow. Two columns. 0 minus 0. No, the difference is 0 and the borrow, you don't need to borrow anything. 0. But when you have 0 and you want to subtract 1 from it, what do you get? Well, let's take a look at that. 0 minus 1, right? So when you borrow, what does this become? 1 0. 1 0 is what? That is 2 minus 1. That is, the difference is 1 and the borrow is 1. You guys see that? Difference is 1 and borrow is also 1. Because when you borrowed, it became 1 0, which is decimal 2. Decimal 2 minus decimal 1 gives you a 1. So the difference is 1, borrow is also 1 because we borrowed. Next, 1 minus 0. Well, difference is 1, borrow is 0. That is straightforward. 1 minus 1, difference is 0, borrow is 0. Right? So you got difference and borrows over here for half subtractor. Questions about this? Where does the 2 come from again? Okay, so you see this, when you are trying to do, let me do this, 1, 0, 1, 1, right? And you're trying to subtract. Can you do 0 minus 1? Well, no, you need to borrow. So if you need to borrow, you need to write this as -1 over here, explicit -1 to the left position. But when you complete the borrow, there is a 1 over here, right? So the number itself has changed from 0 to 1 0. 1 0 is what? 2 in decimal, right? So 2 minus 1 will give you what? It will give you a 1. So the difference is a 1 and the borrow is also a 1. This is for subtraction of 2 bits at a time. But I hope you see that we will also need something that can subtract 3 bits at a time. That needs a full subtractor, subtracting 3 bits at a time. So now it includes the borrow, right? So you see this, there is a borrow written up here as well. in the same way as you had carry in for the previous discussion about full adder. So 3 bits at a time, 0, 0, 0 is one possibility, and there are 7 other possibilities taking you all the way to 1, 1, 1. So let us do something interesting. Maybe we can try to do this. So what is 0 minus 1 minus 1? So 0 minus 1 is what? It is a 1 with a borrow of 1, right? Yes. So 0 minus 1 is a 1 with a borrow of 1. Now, 0 minus 1 would be what? You would lose this 1, but you will still have a borrow. So you have 0, sorry, why did I write 0? 1. 0, borrow 1. That's what you have here. You guys see that? 0 minus 1. If you do it as 2 bits at a time, 0 minus 1 gave you 1 with borrow 1. And then because you subtracted another 1 from it, the difference became 0, but the borrow remained as 1. That's how you got that. Let us do something else. So this is easy. This is easy. Let's do the last one. Sure. Let's do the last one. So when you do 1 minus 1, you have difference of 0, borrow of 0, right? 1 minus 1, you have difference of 0, borrow of 0. And then now 0 minus 1 will give you a 1 with a borrow of 1. Using this. You guys see that? So 2, how do you represent a borrow in the number? You represent borrow by literally doing a minus 1 to the left position. So like this. That's your borrow. So you actually put a minus 1 at the bottom to the left subtraction position. So when you do this, it will be 1 minus 1 minus 1. Yes, yes. Which is why we are discussing this, right? You are representing borrows as explicit subtractions. The subtraction is of a minus 1 to the left position. Think about it like this. All right, here. When you did this, right? 90, what was the number? 95 and 16. All right. So when you did that, 95 and 16, if you wanted to borrow, what happened here? I could always do this. I can always do a minus 1 there and then write a 15 there, right? And then once I do that, what do I get? 9 over here. And then 9 minus 1 will give me the 7, right? So I can always do this. Explicit borrow and then the borrow. The difference is 9 and 7. I can always do that. We have just not been doing it that way, thinking it that way. It was not necessary, but now it is necessary to do it with binary. Will it help if we first convert the numbers to decimal, do the subtraction, then convert the result to binary? No. So the goal is not for you to get the right answer. The goal is for the computer to get the right answer, right? So the subtraction still needs to be done in binary, right? I hope you see the point here. Yes. All right, we talked about binary subtraction. Okay, so So far, we are all in the positive world. Can you repeat the part of 0 minus 1 minus 1? Okay, so let's do that. 0 minus 1 minus 1. So 0 minus 1 minus 1, right? Okay, so let's do 0 minus 1 first. What is 0 minus 1? The difference is 0 and the difference is 1 and the borrow is 1, right? Now, you need to do a 1 minus 1. Why? This one coming from here and that one coming from there. So now this becomes what? 0, but the borrow continues to be a 1. All right, let's move on, you guys. Yes, we are into introducing the negative numbers, right? So let's see. 5 minus 3 was fine. 1 minus 1. The difference was 0. Borrow was 0, right? You see, for borrows, when you're doing the subtraction, reserve this last position for a borrows row, right? So that you can write explicit zeros and minus ones over there, indicating borrow or no borrow. So 1 minus 1, difference is 0, borrow is 0. For 1 minus 1. Next, you have got 0 minus 1 minus 0. So from the full subtractor table, you find out that the difference is 0 and the difference is 1, borrow is 1. You write that. Next, 1 minus 0 minus 1. That's a 0. 1 minus 0 minus 1. That's a 0. There's no borrow. So 5, 3, 0, 1, 0, 2. So everything is good here, right? So when we did this, when the result was positive, it checks out. However, let's introduce the first sign of confusion, possible confusion. 3 minus 5. When you did 3 minus 5, you have 0, 1, 1 at the top, 5 at the bottom, you have a minus sign over there. And when you do this with differences and borrows, you will see that the result actually comes out to be 1, 1, 0. What is 1, 1, 0? 6. That's incorrect result, right? You expected that result to be negative 2. But you got 6. A hanging borrow, over here you see there's a hanging borrow there. Hanging borrow tells us that the result is going to be negative. So how can I look at this and say that it is negative 2, which is the expected result? I may be able to do that if I treat this as a sign and I treat this as the number. So negative for 1 and 2 for the number. So I would get the right answer if I thought of those bits as negative and the number itself. But there is a lot more to unpack over here than just that. But I hope you see that there is a very important need to be able to represent negative numbers. Because I can't just do any representation and be able to do the subtraction correctly, do the addition correctly. Some representations work well with that. Some representations will need a lot more things to be able to get the correct answer. Ajit, you have got the right idea. So 0 is 1, 0, 0, 0 and 0, 0, 0, 0 for form of representation, which is called sign magnitude representation. So I'm going to unpack that, all of that in just a bit. But the goal of this slide is to introduce the idea that we need a different form of representing negative numbers. The way we represented positive numbers is not going to work for negative numbers. Hence, we need a way to represent negative numbers. That's what we are talking about here. And there are two ways. Let me take some questions on the chat box here. So 1, 1, 0 represents 6 and negative 2. No. So stay tuned for that discussion. We are going to start representing negative numbers in a different way. How do you represent 1 as a negative? Then how does the computer understand the context? So all numbers will have to be represented in that way. That's how it understands the concept. There's no differentiation, right? All numbers will need to be represented in one form. All we would need is one bit that distinguishes whether the number is positive or negative, right? We only need one bit. So the last digit will either be a 0 or a 1. The leftmost, right? The most significant bit, the leftmost bit. If it is a 0, right, leftmost, yes. If it is a 0, positive. If it is a 1, negative. More about that. Like, just hang on to that. Now, to represent numbers, we have two major schemes. One is sign magnitude, and the other is 2's complement form. You can represent all numbers in these two schemes. All numbers in these two schemes. And we will go through those examples in just a bit. There is also a 1's complement, but that's not of much use. So that's why we are not talking about that. You can still do addition and subtraction in sign magnitude. You can still do addition and subtraction in 2's complement. The difference is when you're doing arithmetic in sign magnitude, you will need a lot more things than what you need for 2's complement in order to get the correct results. So this works, but needs more hardware. This works. So in your computer, numbers are represented in 2's complement form. Just hold on. So here, now think about 4-bit, right? If you have 4 bits, then you have how many combinations? You have 16 unique combinations with 4 bits. And if you want to use that for both addition and for positive and negative, roughly half of them should be positive and half of them should be negative. So the one way to do that is to reserve the leftmost bit for sign of the number. And the remaining 3 bits, you can associate the value of the number with that. Now we are talking about the simpler of the two major schemes first, which is signed magnitude representation. We have a 4-bit example over here. How do you represent +4 and -4? So sign and magnitude, right? The name itself tells you that those are two separate entities. They are not related, they are separate, right? So 1 bit is being used for sign, the other 3 bits over here are being used for the magnitude of the number. So 0, 1, 0, 0 is +4 and 1, 1, 0, 0 is -4, right? So you're using the leftmost position to indicate the sign of the number. So this is where we are going from unsigned representation that we did so far now to signed representation. And as you can see, it includes both positive and negative numbers, right? So sign in the higher order bit the leftmost bit is actually going to indicate positive or negative. 0 for positive and 1 for negative. The magnitude of the number or the value of the number is going to be the remaining bits. So for example, if you have 4 bits in total, then the rightmost 3 bits will contribute to the magnitude of the number. And with a 4-bit example, if 1 bit is being used for sine, you only have 3 more bits to do the magnitude, which means 0, 0, 0 all the way to 1, 1, 1. So you can only represent numbers. What is the range here? 4 bits. You can go from -7 to +7, right? That's going to be the range with 4 bits. In general, if you have n bits, you are going to have -2 raised to n minus 1 minus 1 to positive 2 raised to n minus 1 minus 1. That's going to be the range of bits that you can represent using signed magnitude representation with n bits. You can quickly do some simple examples, right? So suppose you have 4 bits, you can do -7 to 7. 5 bits, you can do -15 to +15. 6 bits, you can do -31 to +31, and so on, right? Now, earlier, remember I mentioned that if we were limiting the number of bits, we would be in trouble. You see, now we have to start talking about the limitation on those bits. So why is this method inefficient? I'm going to talk about that. That's where we are going with this. Yeah, I had the same question. All right. Let's talk about how to represent 0 in sign magnitude form. What should I talk about this? So when I'm doing this slide, you see, I hope you noticed I was focusing a lot on the number of bits. You see that? Everywhere I was talking about how many bits do you have to represent this, right? Why is that? Well, because only when you know the number of bits, you can make the most significant bit treated as the sign. Otherwise, you wouldn't know which one is the sign. If you didn't limit the number of bits, then you would not know which bit is being used for the sign. Two raised to 6. No, it's actually much more than that. So we can represent. So I'll talk about that in just a minute. The 1-bit limitation exponentially reduces computing power. It doesn't reduce computing power. It reduces the number of bits the range of the numbers you can represent. All right. How do I represent 0, guys? Whenever you talk about signed number of bits, need to be number of bits to represent signed numbers needs to be explicitly mentioned. It is extremely important for everyone to understand this. The moment we talk about signed representation, whether it be signed magnitude form or 2's complement form, we need to first fix the number of bits that we are trying to do this with. So, representing 0 in signed magnitude form. How many bits would you like me to do this for? 3 or 4 or 5? Pick 2 bits. All right, so actually I'll do this. I will just so that we understand the difference. 2 bits, 3 bits, 4 bits. With 2 bits, you have 0, 0 and 1, 0. Positive 0, negative 0. For 3 bits, you have that. For 4 bits, you have that. I hope you see 2 things here. One, this plays a crucial role, right? Because you see 1, 0 is different from 1, 0, 0 is different from 1, 0, 0, 0, right? So the number of bits has to be explicitly mentioned, right? All of these are being used for sine, and the remaining bits are being used for magnitude, right? So plus 0, minus 0, plus 0, minus 0, and so on. So that's the first thing that I want you to notice. The second thing that I want you to notice is we are using the same 2 unique sequences to represent the same number. That's inefficient, right? I have, so for example, with 4 bits, I had 16 combinations. So it would be very nice for me to use those 16 possibilities for 16 unique numbers. But if I do this, I'm losing 2 of them for 0, plus 0 and minus 0. The other 15 are fine, other 14 are fine, but 0, I'm losing 2 of them, which is why the range goes from -7 to 7. Because we are losing that, right? So those are the 2 things that I want you to see as issues with sign magnitude. The second issue of 0 being represented by 2 unique sequences is actually just for the sign magnitude representation. We'll talk about that a little bit later. But representing 0, I hope you're okay with that. In sign magnitude, right? Sign and magnitude. First number, remaining numbers. How do you represent -56 in sign magnitude form? What am I missing here? Someone tell me what I'm missing here. What is the one thing that everybody should be? Number of bits. Yes, number of bits is missing here. So how many number of bits should I choose? Do you guys have a suggestion about how many number of bits I should probably choose? Remember, there is a range. So 5, I can only do this, right? You see this? With 5 bits, I can only go from -15 to 15. With 6, I can only go from -31 to 31. How many do I need here? At least 7, yes. So let's do at least 7. So 7 bits, assume 7 bits. What would be the sign and what would be the magnitude? What would be the sign? 1, 2, 3, 4, 5, 6, and 7. I've got 7 positions here. Sign would be 1. Okay, because it's negative. So because this is a negative number, your most significant bit will be 1. That's fixed. All right, now how about the magnitude? I need 56. How can I make 56? 56 equals 32, right? Plus, if I have 16, where do I reach? Yes, plus 8. Sure, I think that's it, right? Right. So it should be 1, 1, 1, 0, 0, 0. You can check that. Yes, 1, 1, 0. Yes, that's what I got. So that's your magnitude. So you've got 1 for sign, and then you have got the magnitude here. 1, 1, 1, 0, 0, 0. So that would be -56 in sign magnitude form. make sure that you understand why we need to do this 7 bits, right? What if you had to do this in 8 bits? What would be the answer if you had to do this with 8? Yes, perfect. 1 0 1 1 1 0 0 0. Yeah. Now you see why we need to talk about the number of bits. You see the answer dramatically changed, right? 1 1 1 0 0 0 to 1 0 1 1 1 0 0 0, right? They are two different numbers representing the same number, negative 56 in sign magnitude. Now let's talk about sign magnitude addition and subtraction. Addition tends to be easier. So I have broken it up into many cases over here. So for example, I've broken it up into operands having the same sign, the numbers that you're trying to add have the same sign, and operands having different signs. So for each of these cases, you have to talk about two things. What is the sign of the result and what is the magnitude of the result? So for example, if I start talking about operands having the same sign, I have got 4 possibilities, right? 4 plus 3, minus 4, minus 3, 4 minus 3, minus 4 plus 3, right? So over here in the top 2, I've got both of them positive or both of them negative. In the next bottom 2, I've got one of them negative and one of them positive. So how do I do this correctly using sign magnitude form? Well, 4 plus 3, when you do that with positive operands having the same sign and positive, then you will get an answer 0, 1, 1, 1. So 1, 1, 1 is your magnitude of the result, 0 is the sign of the result. So what does that mean? Sign of the result in that case is the same as the sign of the operand's sign. Positive because these two are positive. Careful that you're not adding the sign bits. The way you are computing this is by literally looking at the sign of the operands. If they are the same, then the sign of the answer is also going to be the same. Don't add the sign bits. So you have to follow a few rules if you want to get the correct answer in sign magnitude form. Similarly, for negative 4, negative 3, the answer is 1, 1, 1, 7, and the sign of the answer is sign of the numbers. So this is 1 because these two are 1. So when we do this, we have to talk about two things, right? Sign of the result and magnitude of the result. Magnitude of the result is the magnitude that you get from the addition. Sign of the result is sign of the operand's sign. And because operands have the same sign, there's no confusion about what it is for the top 2 cases. Now let's go to the bottom here. Operands have different signs. This is where the most confusion happens. In order to get the correct result, when you are doing sign magnitude addition with operands having different signs, then the sign of the result is the sign of the operands with the larger magnitude. What does that mean? That means I need a comparator. I need a comparator to compare the two numbers, and whichever one is the larger of the two, I need to notice the sign of that number, and I'm going to associate that particular sign with the sign of the result. So 4 is bigger, that's why positive. 4 is bigger, that's why negative. You guys see that? So the sign of the answer is sign of the larger number. In this case, 4 was the larger number, which is why when we did 4 minus 3, 4 was positive, so answer was positive. When we did negative 4 positive plus 3, we did negative for the answer because 4 was negative. Okay, how about the magnitude of the result? For magnitude of the result, you need to do subtraction. So the same subtraction rules that we saw earlier using the half subtractor and the full subtractor rules. So you would have to do explicit borrows and carry out the subtraction. So to get the magnitude of the result, you need to do subtraction. For you to get the sign of the result, you need to do the sign of the operand with the larger magnitude. Be careful. In order to do this, you cannot add the signs. You are writing the signs separately. Also note that when you are doing this, write the larger number at the top. So when you have the case of minus something plus something, write the larger number at the top and then subtract. And the comparator that needs to that is needed in sign magnitude arithmetic takes care of that. Larger number at the top subtracted by the smaller number in order for you to get the magnitude. And you can quickly see, if you are starting to work out some examples, and you can see why we need so many rules. Because if we don't follow these rules and blindly just add signs or just subtract numbers as and whenever we want, we will get incorrect answers. The only reason why we were able to get all these correct answers of 7, -7, 1 and -1 here was because we followed those rules. And these limitations are there mainly because of the scheme that we are using, sign magnitude. A lot of these limitations go away when we look at the other scheme, 2's complement form, which is what is used in computers. So sign magnitude form is kind of like a, predecessor. So think of it as this didn't work, so we need to go to 2's complement. How about sign magnitude arithmetic? Now we are doing subtraction. Again, we have all these rules. Subtraction when operands have the same sign. Subtraction when operands have different signs. When you are doing subtraction, so for example, 4 minus 3 or -4 minus 3, 4 minus -3, -4 minus 3, you see the operands are both positive here, the operands are both negative here, the operands have different signs here and here. You're doing subtraction, 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 subtraction. So what are the rules over here? So many rules. That's why we are going to ditch sign magnitude for arithmetic. Sign of the result is going to be the same with addition with different signs. What was that? Right here. Sign with the sign of the operand with the larger magnitude. Okay, so that's what happens over here. Sign with addition with different magnitudes. So you need to take the sign of the number with larger magnitude. Which one is larger, 4 or 3? 4. What is the sign? Positive, 0. Which one is larger, 4 or 3? 4. What is the sign? Negative. Next, operands having different signs. What do you do for the magnitude? We just subtract for the magnitude. But don't subtract the signs, just the same way as we didn't subtract or add the sign bits earlier. How about sign of the result and magnitude of the result? When we are doing sign magnitude subtraction with operands of different signs, the sign of the first operand is going to be the sign of the result. What is the sign of the first operand? 4, positive, 0. 4, negative, 1. You are putting the larger magnitude at the top and then doing the subtraction. In this case, you have to do the addition because the numbers are going to get added in terms of magnitude. Addition to get the magnitude of the result. So in all of this, you see, we need a few things, right? We need something to add. We need something to subtract. We need something to compare. Right? So that's kind of the problem here. We need too much to get the right answer using sign magnitude representation, which is why we move to 2's complement form. But what is the advantage of sign magnitude representation? It is very simple to represent in sign magnitude representation because there is a separation between the sign and the value of the number itself. Sign and the magnitude are treated differently. Now, when you do these additions or subtractions, you could end up in overflow conditions. What does overflow mean? Overflow simply means result falls outside range. How many bits are we using over here to represent the numbers? 4, 4, 4, 4, right? All of the numbers are 4 bits each in this one. Okay, so if you have 4 bits, what is the range? Range with 4 bits for sign magnitude form. 7 to negative, okay, so I'll say -7 to 7. Yes, -7 to 7, right? That means if your answer, the result of that arithmetic falls outside this range of -7 to 7, that indicates overflow. That means the number of bits, 4, are not enough to represent that number in sign magnitude form. Magnitude is too large to fit the number of bits, n-1, because we are losing 1 bit for the sign. So you see, where are those cases? 5 plus 3, you got 8. 8 is outside the range, you got overflow. -5 minus 3, you got -8. Outside the range, overflow. When you did 5 plus 2, 7, that is inside the range, no overflow. And when you did -5, -2, -7, inside the range, no overflow. You see that? So when your answer is within the range, you get no overflow. But when your answer goes outside the range, you will get overflow. Another way to quickly verify this is a positive number plus a positive number, you got a positive number. Hold on. No, that doesn't work for this guy. Actually, that works for sign magnitude, 2's complement. Another way to figure out whether overflow has occurred or not is to observe the carries. So if there is a carry, overflow occurs when there is a carry into the sign position. You see, there is a carry into the sign position. Carry into the sign position. No carry into the sign position. No carry into the sign position. So only for sign magnitude arithmetic, if we keep track of carries in the sign position, carries into the sign position, if it's a 1, that indicates overflow. If it's a 0, that indicates no overflow. But it is because of, so overflow occurs due to what limitation? Number of bits, absolutely. The range, which is the number of bits, right? Yes, the range, but it is due to the number of bits that we have limited. So overflow is because of limitation of number of bits. And we said the moment we start talking about signed representation, we need to fix the number of bits. We need to talk about explicitly the number of bits. What does that mean? That means that we need to worry about overflow every time we think about signed representation, whether it be sign magnitude or whether it be 2's complement. The way you detect it might be different, but we need to worry about overflow all the time. Is there a way for me to get rid of overflow? Sure, yes, you can get rid of overflow by just extending by 1 more bit. If you make these bits from 4 bits to 5 bits, but have the same numbers, you will not have any overflow for 5 plus 3 or 5 plus 2 or 5 minus 3. You will not have an overflow if you extend the number of bits by one bit position. Sure, there is a way to get rid of it. Or you could go for smaller numbers so as to not go into overflow. Okay, so let us stop over here And when we meet next, let's see. When are we meeting next? No, Tuesday, Friday. Yes. So we are meeting Friday, September 11th next. That is when we will talk about 2's complement numbers. So I'm going to see you guys on Friday.